Hello everyone and welcome back. In the beginning of the semester we started out with our first unit on electric fields and electric forces. Our second unit was then on magnetic fields and magnetic forces, and we finished that up last time with AC circuits. Today we're going to start our third unit, which is all about optics. And our next section, section number 24, is about electromagnetic waves. First of all, let's talk about what are waves. Well, imagine that you're holding a long string or a long chain or something like that. Well, we don't have to imagine. I've got one right here. Let's imagine that you move one end of this chain up and down very quickly, something like this. What happens? Well, you make an oscillation that propagates down through the chain or the string. You create this thing that moves through the material that we call a wave. And if I were to do this and continue to move my hand up and down, well, if I didn't lose that end of it over there, I would make a wave that propagated down through the chain. Well, let's take a look at the electric and the magnetic fields. Let's imagine that we have a charged particle. Let's just say a positive charge. And I'm going to hold it over here. Let's imagine we hold it here. So I've got this positive charge over here. We know positive charges create electric fields, and electric fields point away from positive charges. So let's imagine we're looking over here. What does the electric field look like due to this positive charge? Well, it's going to point away from that positive charge. But now let's imagine I take this charge and I move it upward. What's going to happen to that electric field? Well, as that charge goes up, the electric field is going to start to point down. And then if I were to move this charge down, this electric field would point up. So if I were to move this charge up and down and up and down and up and down, the electric field over here would point down and up and down and up. I want to think about what's the change in the electric field. We have this overall electric field that points away, but then on top of that, we have an electric field that's going to point down and then up and down and up and down and up. So we have an oscillating electric field that's oscillating in an up and down direction. Okay, very good. Now, let's think about as I move this charge up and down over here, let me just draw that motion over here. As that charge is going upward, that's a moving charge, and that is a current, and that is a current in this direction. Moving charges, in other words currents, create magnetic fields. So there's going to be a magnetic field created over there. Let's just think about as the charge is moving up, what's the direction of the magnetic field over there? The direction of the magnetic field is going to be into the board. So point our thumb in the direction of the current, our fingers over there point into the board, like that. Very, very good. Well, as the charge moves down, we'll then have a current downward and the magnetic field will point out of the board. So we'll have an oscillating magnetic field that points into the board and then out of the board, oscillating in, out, in, out. And if I continue to move this charge up and down and up and down, we'll create these oscillations in the electric and the magnetic fields that propagate off through space in that direction. Excellent. Let's draw a picture of what this oscillation in the electric and the magnetic fields look like. What we get is something that looks like this. We get an oscillating electric field that goes up and down and up and down, while we get an oscillating magnetic field that goes out and in and out and in, from the page. Notice when the electric field is up, the magnetic field is out. And when the electric field is down, the magnetic field is in. This is a little difficult to visualize here because we're trying to represent a three-dimensional structure in just a two-dimensional page. So think about this electric field going up and down and up and down, the magnetic field then coming out of the page, in, out, in. And notice that the electric field and the magnetic field are both perpendicular to the direction of the wave, which is in this case to the right. So the electric field is perpendicular to the magnetic field, and both of them are perpendicular to the velocity vector. Very, very good. An individual by the name of James Clerk Maxwell, who lived from 1831 to 1879, was looking at all of these equations that dealt with electricity and magnetism. Things like Coulomb's law and equation that describes how much magnetic field is created by a current, things like that. What he did was put them all together into four fundamental equations, what we now refer to as Maxwell's equations. They are the fundamental laws that describe electricity and magnetism, like Newton's laws describe the fundamental equations for mechanics. One thing that Maxwell discovered was that if he solved those equations for an oscillating electric and magnetic field in a vacuum, it turned out that all of those waves had the same speed. And the speed of those waves was a very simple result that depended on some constants we've seen before. The speed was, and he did this actually in 1865, the speed, it turned out, was 1 over the square root of epsilon naught mu naught. If you remember, epsilon naught is the permittivity of free space. Mu naught is the permeability of free space. Epsilon naught dealt with electric fields, mu naught dealt with magnetic fields. And the speed of these waves was this very simple combination of those two. We can put numbers in there, and what we find is that 1 over the square root of epsilon naught, 8.85 times 10 to the minus 12, Coulomb squared per Newton meter squared. Mu naught, 4 pi times 10 to the minus 7, Tesla meter per amp. Put that all in there, and what we find is that this equals 3.00 times 10 to the 8th, and you can work out those units. They just turn out to be the simple units for a speed, meters per second. It doesn't matter any other properties of the waves, they all travel at the same speed. This number turns out to be so important that it has its own symbol. And you might have seen this symbol before, we'll talk more about it later. It is the lowercase letter c. C, 3.00 times 10 to the 8th meters per second. And what is this? This is, so let me back up a second. What Maxwell noticed was that this value was a number he had seen before. This was very close to the experimental value for the speed of light. What Maxwell surmised from that, and he surmised correctly, was that light was an electromagnetic wave. He was the first person to discover that, and he did by solving for that speed of an electromagnetic wave and found it to be the same as the experimental speed for light. So this number c, 3.00 times 10 to the 8th meters per second, we'll refer to this as the speed of light in a vacuum. The speed of light in a vacuum. Sometimes this is written as SOL for short, which stands for speed of light. It doesn't stand for something else, it stands for speed of light. So let's remember C, 3.00 times 10 to the 8th meters per second. For my students in my class, just keep in mind, this is such an important number, I am not going to give you this constant on a quiz or an exam. I expect you to remember this one. There aren't many constants I expect you to remember, but this is one of them. 3.00 times 10 to the 8th meters per second. Excellent. Now, let's just think about this for a second. Tell me something about that number. 10 to the 8th. That is a very, very large number. If we were to write this out, this would be 300,000,000 meters per second. 300 million meters per second. In other words, taking out a factor of 10 to the 3, this would be 3 times 10 to the 5th kilometers per second. In other words, 300,000 kilometers per second. So 300,000 kilometers, that's a very, very long way every second. That's how fast light travels. To give you an idea of how fast this is, it only takes light about 8 minutes to go from the sun all the way to the Earth. 93 million miles, it only takes light 8 minutes to get here. It is very, very fast. As a matter of fact, it is the fastest thing that we know of in the universe. The fact that all light in a vacuum travels at this speed allows us to use certain characteristics about light to characterize different kinds of light. Let's imagine we go back to our charge. If I were to move this up and down very slowly, and the light propagates away at the same speed, if I move this up and down slowly, I will end up with a wave that looks very long. A very long, slowly changing wave. Whereas if I were to take this and move it up and down very fast, the wave would still propagate away at the same speed, but now I would have a wave that oscillated up and down much more rapidly. We can distinguish between waves like this using a couple of different characteristics. First of all, the distance between two consecutive peaks. We'll call this the wavelength. The wavelength of the wave. And we will describe this with the Greek letter lambda. So this is a Greek letter lambda, a lowercase lambda, as a matter of fact. So lambda is the wavelength, the distance from one point to another similar point on the wave. The units of the wavelength, because it's just a distance, are meters. So the units of wavelength, the units of lambda, are meters. Now notice that the distance, if I have a sinusoidal wave, the distance from peak to peak, and these points are sometimes the maximum points on the wave, these are sometimes referred to as the peak. The distance from peak to peak, or maximum to maximum, the wavelength, that's the same as the distance from a valley to a valley, or the trough to a trough, the minimum to a minimum, that's the same distance. Or from some point where it's in the middle to another point where it's in the middle, but not the next point. We have to go from a point where it's in the middle when the wave is going down to a point in the middle when the wave is going down. So always from one point to a similar point, a point that looks the same on the wave, the next consecutive one. That's the wavelength of the wave. Something else that we'll use to characterize waves, imagine that this wave then is propagating down through space, and we are over here watching this wave go by us, and we count how many of these waves, say this is one complete wave, how many of these waves pass us every second. So as the wave is propagating by, we count 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. How many complete wave sections pass us every second? That is referred to as the frequency. The frequency is the number of waves per second that pass us by. The symbol that we'll use for frequency is a lowercase f. And the units of f would be waves per second, or oscillations per second, or cycles per second. That is a hertz. Capital H-E-R-T-Z. The short form for hertz is a capital H, lowercase z. So luckily we won't confuse that with something else for H like henries, because we've got that lowercase z in there. So the units of frequency are hertz. Very good. Now let's imagine we're looking at a wave passing us by, and we'll think of just a more simpler wave like a water wave or something like that. Let's imagine that we can take a look at the wavelength and frequency, and let's see if there's a relationship between them.